This is Nagalakshmi. I am working as an assistant professor in Department of Information Technology at LIET Institute of Engineering and Technology. Today, we are discussing about Warshall's algorithm using dynamic programming in design and analysis of algorithms. Before we begin the discussion on Warshall's algorithm, let's see why it is essential and what is the important in the design and analysis of any algorithm in terms of time and space complexity. It has many algorithms to find minimum cost or to find minimum path. There are so many algorithms are there in a DAM. So preferably we will take a few algorithms to find the minimum path. Those are multi-stage graph algorithm, all-page shortest path algorithm, and Prim's and Kruskal's algorithm, and etc. So all algorithms have their own advantages and its limitations. To solve specific problems, we are using this kind of algorithms. Suppose we are using Warshall's algorithms in using dynamic programming in design and analysis of algorithm. So we'll start our session on Warshall's algorithm. Let's begin our topic, introduction about Warshall's algorithm. So Warshall's algorithm is mainly used to determine the transitive closure of a directed graph for the possible paths, all pairs of a paths. Okay, let we see that Warshall's algorithm mainly used to find the transitive closure. It generates some sequences of matrices of size n. Here n represents the number of nodes, or we can say it's a number of vertices also. Here we are giving a R. R is nothing but it's a relation of an adjacency matrix. R is nothing but a transitive closure of a relation. So let we consider here RO, R, K minus 1, R, K and Rn. These all are nothing but the adjacency matrix of each and every node. Here R0 is nothing but our original adjacency matrix of a graph, and then K minus 1 is nothing but there is a next node. If suppose here R0, R1, R2 and so on so Rk minus 1 and Rk. So till 0 to n vertices. So here now we are going to find out the sequence of vertices used to define a path in a simple graph. So let here we already mentioned what is a kth matrix. In the kth matrix, Rk and Rijk is nothing but a relation of a matrix of root via. The elements defined at the ith row and jth column will be 1 if it contains a path from Vi to Vj. What is Vi and what is a Vj? Vi is nothing but a source node, and Vj is nothing but we can say it is a destination node. Where coming to a K is nothing but a via node, or else we can call it as an intermediate node. Let's move to the next node. Here we have a formula to find the transitive closure of an adjacency matrix, and here we have Rijk is 1 and here we have Rijk minus 1 is 0. So what do you mean by a 1 and 0? Here if suppose we have a root directed node from Rij to Ri to Rj, then we are considering it as a 1. If there is no path between I and j, then we are considering it as a 0. So that is the formula where we are going to find that relation R. So let we see a small algorithm to find an adjacency matrix. Before going to that, we will find that what is the complexity of this an algorithm. Let's consider an algorithm. Here there is a small piece of code, or we can say it is an algorithm. There are 3 loops are there. So here, so that we can find the complexity like n into n into n. So here we can find that f of n is an n cube. So the time efficiency of this algorithm is n cube, and where the space efficiency is also coming to that n cube. So where theta of n cube is in a worst case of the theta of n cube is a time complexity of an algorithm. So whereas we can consider this as a name theta notation for asymptotic notation. So here we can say that brute force algorithm is better than Warshall's algorithm. Let us discuss the example of transitive closure. We consider this graph. We'll be having a 4 nodes, 1, 2, 3, 4. Here we have to give the numbers 1, 2, 3, 4, and the number of columns are also a 4, like 1, 2, 3, 4. Here we are giving a values like 1 to 2. So is there any direction from 1 to 2? No. So that's why here we need to consider it as a 0. Then let us we consider like 1, 2, 3. There is a direction, so that we have to give a transitive closure as 1. Likewise, if there is a path between one node to the another node with the directed graph, we have to give a number as 1. If there is no direction, so then we can consider it as a 0. So this is an adjacency matrix for this graph. Let us consider the second graph. Here we have nodes from 1 to 3, and we have from 2 to 1, and we have from 2 to 4 and 4 to 2, and we have considered 4 to 3. Right? For that transitive closure, we can give like 1 to 1. There is no path. So that's why we have given 0. If suppose we are considering like 1 to 3, yes, there is a path. So here 1 and 3 will be having a path called 1. The same way here we can consider 2 and 1. Is there any path between 2 and 1? Yes. So that's why we have to consider it as 1. Likewise for 3, 4 rows as well as 1, 2, 3, 4 columns. We need to consider that all the rows as well as the columns, we need to assign the numbering like zeros and ones. This is an adjacency matrix for this particular graph. Let us see the formula. So where R is nothing but a relation, K is nothing but an intermediate vertex, where I and J is nothing but source and destinations, or else we can consider it as an rows and columns also. I and J are nothing but rows and columns. Here we can say that K is nothing but a intermediate vertex, where you can traverse from I to K and K to J. So here we are considering intermediate vertex. What exactly an intermediate vertex? So the name itself, it is there, Warshall's algorithm. Warshall's algorithm is nothing but to find the transitive closures of an all ordered pairs. So now we are going to find ordered pairs for all the nodes. Let us consider a graph generating a matrix using Warshall's algorithm. Here we have 4 nodes A, B, C, D. These are the vertices of a graph. And here we can see that number of rows, number of columns, and based upon the directed graph we have assigned a transitive closures. So we already discussed about that how to give a numbers either zeros and ones. If there is a path from one node to another node, then we have to assign a 1. If there is a no route from one node to another node, then we have to assign a 0 value for that. Right? Now we are going to consider the 4 transitive closures for this graph. How means by using of an node, intermediate node as A, by considering of intermediate node as B, nothing but R1, R2, B, and there are vertex A is nothing but comes under R1 in a relation. Intermediate vertex B comes as R2, intermediate vertex C comes R3, and intermediate vertex D comes R4. Let us we give the numbering for the 8th row and 8th column, 8th row, bth column, 8th row, 6th column, 8th row and dth column. Here we have a root from A to B. So that's why for A to B we have given 1 as a value. So remaining zeros will be means that there is no root for that A to C, A to D and A to A. So now what we have to do, we need to find, let me see R1. How do we find? By making of intermediate vertex A for R2, considering intermediate vertex as B, for R3 considering intermediate vertex as C, for R4 considering intermediate vertex as D. Next, we have intermediate vertex A. So, always remember that whenever we are finding a adjacency matrix in a relation R0, R1, R2, R3 and R4, we need to get the data from the previous adjacency matrix. That is why we have represented Rk minus 1. So, k minus 1 is nothing but adjacency matrix of a previous result. So here we can see that R0 is nothing but our original graph adjacency matrix. We are considering intermediate vertex A from the previous graph R0. We should not disturb 8th row and 8th column. Remaining will be having zeros. And where are those zeros? C to B, C to C, C to D, as well as B to B, B to C, and D to B and D to D. So wherever zeros are there, we need to convert that transitive closure. How means? By using the formula we have already discussed in the previous slides. Now we are finding a transitive closure for B to B. How? By giving a intermediate vertex A. Here B to A. What is the B to A? B to A is 0. What is A to B? A to B. A to B is 1. So here 0 and 1. 0 and 1 will always gives the result 0 only. Whereas if the value is like 1 and 1, if the value is 1 and 1, then only we will get a 1. Either of the value is 0, then we are going to consider as 0, because of here we are using an AND operation. Yes, sir. Let us consider that intermediate vertex as B. So this is from the previous transitive closure. We are considering it as an R1. Now what we have to do? We need to fix B. We need to freeze Bth row and Bth column. We should not disturb the B and B. So now wherever the zeros are there, we need to change to that transitive closure, and wherever the 1 is there, keep as it is. So here we have A to A to C, A to D. So how we can take? By using of A to B and B to A. So what is the value of that from the previous one? 1 and 0. So if it is 1 and 0, we need to provide it as represent it as 0 only. If suppose the value is 1 and 1, then we have to represent it as a 1. So here again we have two modifications. Where are those modifications? Means from A to D and D to D. So this is the next transitive closure, nothing but R2, if you are considering as intermediate vertex as B. From the previous slide, we have got R2. So now we need to consider this as a base for the finding of intermediate vertex C. So now Cth row and Cth column is fixed. So now wherever the zeros are there, we need to convert that into a transitive closure. So for that we have A to A is 0. So that's why we need to convert. What is the intermediate vertex? Intermediate vertex is C. So that's why we have to put A to C and C to A. Here is also a transitive closure is 0 and 0. I already told you, if it is either of a value is 0, we need to get it as a 0 only. If both the values like a 1 and 1, then only we will get as a 1 as a transitive closure. So this is a resultant of that intermediate vertex C. Let us consider the intermediate vertex D. From the base of R3, we have to find out that R4. How we can able to do means by freezing the dth row and dth column. Dth row and dth column. Let us consider intermediate vertex D. So this is R3, means we got a from previous slide. So where we are going to find intermediate vertex D by using of this D. So here dth row and dth column is fixed. So wherever that zeros are there, we need to convert that into a transitive closures by providing the intermediate vertex D. So here we are finding for A to A is 0. So A to D and D to A. So what is that A to D? A to D is 1 and D to A is 1. So here 1 and 1 will give us 1. Similarly, for all the zeros of that R3, we are going to find or we are going to convert that into a transitive closure if possible. So here all are the vertex 4 we have found. So this is our final matrix form, nothing but our transitive closure. So let us consider that previous slides we have row 1 and 2. So what do you mean by row 1 and 2? Whenever R1 is nothing but from the previous slide like R0, nothing but base form. These are the transitive closures what we have calculated from R0. From R0 to R1 is a transitive closure. From R1 to R2 a transitive closure. From R1 to R2 to R3 is a transitive closure. From R3 to R4. So the R4 is nothing but our final transitive closure of a Warshall's algorithm. Nothing but where you have found the transitive closure for all pairs. This is our final adjacency matrix of a given graph using Warshall's algorithm. So we can say it is a transitive closure of a Warshall's algorithm. I hope this session will help you. If you have any doubts, please comment. For more videos, please subscribe our channel. Thanks for watching.